transistor, pretty difficult, a lot of things. And then we study the delay of the wire. After that, we study the basic logics, right? We study the CMOS static logics. We know how to calculate the delay, their capacitance, their resistance. And then we study the domino logic. There are more different logics that mentioned in the textbook, but we did not cover. Right? Now, with this, our goal is to build a larger system, right? And the first thing is the arithmetic building block, right? How do we do addition, subtraction, multiplication, division? All these things are very important in the CPU, right? So we all know that a CPU is decomposed into a few parts, but the most important thing is a data path and memory. The data path does the computation, okay? And the memory store the information. And in particular, when you're doing about machine learning, we have a lot of data that you need to communicate between the data path and the memory. Because in the memory, the computation unit and the memory. This memory mostly is referring to, in this context, more is referring to the SRAM, the cache that is very close to your ALU. Usually our memory consumes a lot of area, it's very expensive, like 50% of the CPU die. And you can imagine if your CPU is selling you for $1,000 each, $500 goes to the memory, but that is the memory on the die, okay? So usually you don't have enough memory, make it into different level. That is not what we're going to discuss here. I don't know if you have learned about computer architecture in other classes. You will talk about the cache, L1, L2, L3. And outside of this cache, which is SRAM, you will go to the DRAM. You get more and more memory, eventually go to the hard drive, right? But they are slow. You don't want to do that. But how do you swap the memory between the hard drive and the DRAM and the SRAM? You need to have a good strategy, right? So you need to have something called caching. So if you try to find for something, you bring in the neighbor because you know there's a high chance you may read the neighbors, right? So then you can reduce so-called cache miss. Once you miss something, you need to wait of many cross cycle for the DRAM to bring in the memory, right? And that's why at the beginning of the class, I also talk about the new emerging memory, right? So if this is SRAM, right? And then you still need to go through the DRAM, which is cheaper and higher density. And then you go to the hard drive, right? But nowadays we say, hey, can we insert something here? For example, ferroelectric memory. Sorry, I should say MRAM, magnetic RAM memory, which is already in a very good shape in the production already. They are long volatile, and at the same time, they are very fast. Not as fast as SRAM, but they can be smaller than SRAM, also consume less electricity and long volatile compared to SRAM. And between DRAM and hard drive, of course, now we already have this flash memory, right? And we even may be thinking that we add something called resistive memory. Again, they are long volatile. So they were able to make this memory exchange much better. Okay, so that is what people are doing. Now, if you think that you will be a circuit designer, in the future, you also need to think about how to communicate with this efficiently. You have circuits to control to resistive memory, to control the DRAM. For those, if you had taken EE222 with me, we discussed a lot about flash memory, resistive memory, magnetic memory, right? And these are all the future, right? But no matter how good it is, the architecture we are looking at is used the so-called von Neumann architecture. We separate the memory and the data path. So whenever we need something, we need to take the memory, take something from memory and do the computation. And I told you that in the server, in all the Google server, they consume 50% of the energy just to transfer the data between the memory, all this memory to the data path, right? And also a lot of delay time for that, right? So that's why now people talk about in-memory computation. Can we actually do computation in the memory or on the data, or put the memory in the data path? So I don't need to exchange. And that's why it come up with the so-called neuromorphic computing, right? So that is another topic. But this is because a lot of data, we are in the big data era, right? We do a lot of machine learning, right? So, but no matter what is done, our goal is to optimize the PPAC, remember, power, performance, and area, okay? So nowadays, here just to say that the delay, area, and power consumption, they are actually bottlenecked by this SRAM. Because I don't have enough memory here, I need to keep communicating with the DRAM. Even for the high bandwidth DRAM, like in the NVIDIA GPU, they're very close, they are very fast, but still not as good as DRAM. That slows down the process. Okay, so perhaps this picture in mind, it will be good, right? And for us, still, we are talking about von Neumann architecture in this class. Okay, any questions or comments? If no, then let's go to here, just a summary of what we said, right? For a CPU, basically, we have a data path where you do the addition, multiplication, shifter, and comparison. And we also have a memory part, the SRAM, right? They're on the same die, very fast, right? Of course, we need to control it. It's the finite state control machine, and interconnect is important, right? So here later we'll talk a little bit about SRAM. Control, we are not going to discuss. This is more in the computer architecture level, right? Interconnect, oh, okay, we discuss a little bit. So mostly we're discussing the arithmetic unit. And the project is about building an adder. So what is the scheme? I think you already know. The scheme is that we build the cell for each bit and then connect them together. So this is a so-called bit slice organization. That can extend if you have one bit that is finished, you can extend to 64 bits, 128 bits, 256 bits, as much as you want, as long as your software can support it, your OS can support it, right? And your energy can, your heat thermal management can support it. Okay, that is the so-called bit slice. So as a result, we will look at one bit, right? We will spend a lot of time just to understand what is 1 plus 1. Once you know what is 1 plus 1, the rest will be just a cascading all the bits together. Okay. So let's start with the most basic thing, the adder. This is a 1-bit full adder. Why is it called full adder? It's because it has the carry out. Okay, so basically what's the adder 1 bit, right? We look at what is 1 plus 1 in binary. Yeah, you have two input, A and B, okay? Sorry, I said something wrong. What I mean the full adder is you have the C in, right? And then you also have the carry in from the previous node, right? C in, previous bit. Then you add them together, you will get a sum. Of course, if you go back to ask a first grader, what is the sum? It will tell you 1, 1 is the sum, right? But in our terminology, we don't call this sum, we call this one the carry out. Because this is the one going to fit into the next highest significant bit, right? Okay, so we have A, B, C in as input, and then C out and sum as the output. Now, if we look at the truth table, A, B, C, these are the input. 0, 0, 0, the output will 0, 0, right? 0, 0, 1, output will 1, 0. This, you know all of them already. In particular, 1, 1, 1, you know output is 1, 1. The sum is 1, C out is 1, right? In particular, you also see something called propagate generate, which I will discuss later. Okay, let's just ignore it for now. Let's just do a very simple, naive way of understanding building the logic, right? So what is sum? How do you write it as a logic? Well, if you look at the sum, you will get 1. If you have 1, 1, or 1, or 1, 1, 1, you have odd number of 1. If you have an odd number of 1, you will get 1. So naturally, then you will see that, oh, this must be A exclusive B exclusive C in. Right? That is when it will give you 1 when it has odd number of 1, right? Exclusive OR means what? Exclusive OR. Exclusive OR means that you cannot have the same number. If you have the same number, output is 0. If you have different, output is 1. So the first time, if you get only 1 A and B, right? Then the second time you exclusive, if you want to get 1, you need to be form an odd number of 1. You just check it out, you will see that. Okay, so this is the sum, right? This is how we understand. So let's just do an exercise quickly, right? If you have any question, stop me and let me know. Okay, so what is A exclusive of B? A not B plus A B not, right? The whole thing exclusive of C in. And I continue to apply the definition of A not B and of this exclusive. Then I try to knock the whole thing first. A not B plus A B not, okay, C in, and then plus A not B plus A B not, the whole thing, C in not. Okay, so not too difficult. I need to use De Morgan's rule, apply this top bar into it, then it becomes, I just do all the way to save time, okay? This way, right? If you don't understand, let me know. C in plus A not B plus A B not C in. Is this okay? Because I applied this one to here, then this becomes multiplication, and then I keep applying to A not B, then it becomes plus, right? Not cancel not, then I have this one. Okay. Then I continue. The main point here is this is A bar. What is A bar? Can someone tell me?
0.
0. Very good. Because one of them must be 0, right? A bar and B bar. So this one too will be gone. Okay. And then we have this one. Right. I put lots of math, but I just want to practice one more time. Then you get A, B, C in plus, I try to arrange them now, right? A bar, B bar, C in plus A bar, B, C in bar plus A, B, C in bar, right? So this is the logic that we have, and this is exactly what we say about odd number of 1. Each of these has odd, will be 1 if they have odd number of 1, right? 1, 1, 1, 1, 1, 1, 1, 1, 1. Some of you may say that I'm wasting your time. Why don't you just use the truth table? It's the same. Yeah. So let's do another way to do that. How about C out? We try to use the truth table, right? So and then the not truth table, I mean the Karnaugh map, right? The Karnaugh map is how do you do it? 1, 2, 3, 1. I put this as AB. This is C. So what do? I start with 0, 0, 0, 1. But next one is 1, 1 because I only switch one number at a time. Okay. And then the next one is 1, 0. This is 1, 0, right? So based on this one, AB is 0, C is 1. Of course, the C out is 0. I don't have carry out, right? AB is 0. C is 1. carry out is 0, right? So similarly, I know that I get C out if I have more than 2, 1, right? So this is 1 or no? No, a lot more than, yeah, more. Did I say something wrong? Yeah, I see something wrong, right? That's why this should be 0, 1, okay? So this is only 1, 1, so this is 0. Here I have 2, 2, right? And more or equal to 2, right? So this is 1, right? When AB is 1, 0, C is 0, this is 0, right? So I do the same thing, I get this. And then if you remember, we will group them. This will be one group. This one give us what? A, B, C. No, I mean C, C, A, B. This one gives us A, B because C is varying 0 and 1, right? This is another group. This one, you see that is the A changing, so it's B, C. Both B and C are 1. This group is only the B changing, right? A and C are 1, so I have AC. Right? So this is another way for us to find out what the equation is for C out. Right? So this is just a review.
Professor?
Yeah.
In the top left-hand corner where it says AB and then /C, does it matter? Like, could it be A and then /B, C? Or should
you can do that. If you A/B, C, then your row will be 4 rows.
Okay.
Yeah, this is AB. It means column is two bit, right? So you have 4 values. If you put B to the bottom, then it becomes BC. Then you have 4 values also.
Got it.
But here it becomes 2.
Okay.
Yeah, so this is a good skill. If you forgot, just Google to learn again. Just doesn't have to go too deep, right? I promise you, I'm not going to test this in the exam, but it's a good skill to learn about it if you have not learned before. Okay. Now, so we know the logic Boolean operation for S, right? A exclusive B of C, and C is this one, CL. Right? Yeah, just quickly tell you why the Karnaugh map, if you forgot. Actually, I also learned it again when I was teaching this class a few years ago, right? You see, we try to switch from 0, 0 to 0, 1. Instead of 1, 0, we go to 1, 1 first. That is because for this gray coding, they try to change it only so that every time when you go from one to another, you only change 1 bit. So from here, 0, 1 to 1, 1, you only change the first bit, 1, 0, 0 to 1, okay? If you have 0, 1 to 1, 0, you have 2 bits changing. This was very important in the past when they do telegraph and for other purpose, because to avoid the noise, they don't want to switch 2 bits at the same time. Okay, and then, but that fit into the Karnaugh map very well. So you need to do this. So now we only have a simple table, right? If you have a more complicated table, 3-dimensional or whatever, right? You also need to be careful of this. So what you're saying that is, see that you say you try to repeat 2 in this way, 2 on, right? The first bit, 2 on, 2 off, 2 on, 2 off, 2 on, 2 off. Do you see that? So after you did that, you will have this property. Then how about the second bit? 4 on, 4 off, 4 on, and then 4 off. It is cyclic, by the way. This is called cyclic. Okay. When you go to 15, 1, 0, 0, 0, you just change the first thing to 0, then you go back to 1. Okay. And same for the third bit, you will see that you have 8 on and then 8, 0. Okay. Okay. Just hope that to let you know what's going on, right? But anyway, we know how to do full adder. Any questions? But we don't want to stop there, right? When we are doing design, the insight is the most important thing. Okay, so we are start generating some concept, not just look at those very messy and confusing algebra. We try to generate something. So I want to generate, create some symbol. For example, generate. This is just a logic. Okay, so generate, I give it a symbol called G. Its concept is that even the input is 0, I still have output. Right? If the C in is 0, C out is 1, what does it mean? It means the adder, the AB, generates a carry out. Right? That's why it's called generate. Okay? So we can look at this. You do see this type of situation, right? For example, C in is 0, right? For the first row. C out is 0. No, this does not generate. C in is 0. C out is 0. No, this doesn't generate. C in is 0. C out is 0. No, doesn't generate. C in is 0. Hey, C out is 1. Yes. Yes. It does generate, right? So generate naturally will be equal to AB. Do you agree? When both A and B equal to 1, I don't care what is the input. I'm going to generate a carry out. I don't care what is the carry in, right? From the previous bit, I'm going to generate a carry out. Is this okay?
Yes, sir.
Thank you. And similarly, right? Even the C in is 1, C out is 0. What is that? Okay, C in is 1, you see that? Hey, but in this case, C out is 0. It deletes my input, C in. This is 1. Okay, C out is 1. No, it did not delete it, right? C in is 1. C out is 1. C in is 1, C out. No, it does not delete. So it deletes when? What happened? When both A and B are 0. When both A and B are 0, you delete whatever come in. Okay, so a delete logic is A bar times B bar if you want to implement. Okay, and there's something called propagate. Propagate, what does it say? It means if even it does not generate, okay, even it does not generate, okay, if input is 1, output is 1. Let's look at this. This one generates, so we don't care. But look at this. This guy does not generate, right? When input is 0, it does not generate. But it will just, if the input is 1, C is 1, it will propagate. So there's some action, some combination is going to bring the C in to C out. And of course, you also know that is when A bar B or A B bar. And this is nothing but A exclusive B, right? So your input only have 1, 1, it's going to propagate. Whatever you have in the input, I will propagate to the C out, right? So we have 3 different bits that we need to memorize: generate, delete, and propagate, right? If I have this concept, what is C out? Right? We just say that the C out is equal to A B plus B C plus AC. You can prove that it is also equal to P C in plus G. You can prove that, but I did not prove. See, I just write it. How come I know that? Because now I have the concept. How do I get an output? Well, input, the C in is 1, and I propagate, or I generate. Then, of course, the carry out will be 1, right? So this will have a higher level of meaning, and then you will be able to design your adder or analyze it easier. Make sense? How about S? S equal to A exclusive B exclusive C in. Okay, and here we learned that, oh, this is just propagate. or exclusive and exclusive C in. You can, this one is easy to see from the equation because A exclusive B is P. But I can also think it in this way. When I'm going to have a sum, either you don't have input and I have the ability to propagate. It means I'm 0 or 1. Then of course 0 plus 1 is equal to 1. Or you have an input, but I cannot propagate. Okay, you will find that this also makes sense, but it's not so easy to understand. The easiest one is this one, right? How do I have carry out? If I have carry in and I propagate. If I delete, I'm not going to propagate, right? If I propagate and I carry in, or I generate. Okay, any questions about this carry? Clear? Okay, now this one I will ask you to go home to repeat what I have said, but on half adder. So what is half adder? It doesn't take C in. Under what situation do we use half adder? Anyone has any suggestion? Why half adder is useful if there's no C in? No carry in. Well, under what situation there's no carry in?
If it's like
Remember, this is one bit.
addition.
Addition, right? But addition does have carry in, except where there's no carry in.
Okay, would it just be a like a 1-bit addition? Like you're not looking
One
for
bit addition, yes. Or the least significant bit, right? You will have a half adder, and then you go to full adder. You see what I mean? Because for the least significant bit, you don't have carry in, right? So you can reduce the logic, reduce the energy consumption and area by adding half adder first, and then go to full adder. Make sense? So in your project, right, you can just create full adder cell and then just cascade them, but that will waste your time. If you are more meticulous, more careful, you may actually, for the first bit, you use half adder to save the area. Okay. But do it yourself at home, right? So once we have the full adder, right, or the bit of an adder, we can start doing addition. And it's very natural. Addition is nothing difficult for you, right? You know that since you are first grader or even kindergartner, for some of you who are smart, right? But here what we're doing is from left to right, from least significant bit to most significant bit. And it's not difficult. Carry in, add to A0, B0, give me S0, right? So maybe it's better if I give an example, 1, 2, 1, 0, 1, 1 plus 0, 1, 0, 1, okay? This is talking about A0, A1, A2, A3, okay? And this is B3, B2, B1, B0, okay? So 1 plus 1, no carry in becomes 0, right? So this is S0, okay? And then it has 1 here. This is CO0, the output carry out of the 0 bit. So you have 1, 0, okay? And then this one will continue, right? So that is how you do the addition. Maybe this is a bad drawing. S0, right? Is that okay? Right? So you keep propagate. Now, that is exactly what we do as a student, right? We go from right to left, here from left to right. What is the propagation delay? How much time does it take to finish the computation? Of course, I need to wait until CO3 to decide whether it's finished, right? It need to have finished when it reach here, correct? So what is the worst case delay of the n-bit register? So we need to define two things. One is the T carry. Okay, the time to compute carry out, C out of a bit. Another is T sum, the time to compute the S of a bit. Okay, there are different circuits. You will see that later. And at least here, you already see that they have different logic, right? One is C out equal to this, one is S equal to this. So for each bit, it takes some time. I don't know, 100 picosecond, 1 nanosecond, whatever, right? But how long does it take to finish it? Well, if I have an n-bit adder here, I first need to compute the carry out, right? Once I compute carry out, I need to supply to here, then compute the carry out 1, carry out 2, carry out 3. This is very long. During this time, S is done, S1 is done, S2 is done, right? So the main computation will be going from 1 to 3, n minus 1 of T carry. Only at this point. When you reach this point, it takes n minus 1 of T carry computation time. How about here? Well, later you find that computing the sum is longer than carry. Okay, so for the whole thing to finish, it will be n minus 1 T carry plus T sum. T sum usually is larger than T carry. So it means after n minus 1 T carry, I reach here. It takes T some time to finish S3, but S3 is long. At that, when you finish, TO3 already finished. Okay, so based on this, this is the delay equation of an n-bit adder. Very primitive. And you can see that a lot of problem. If I want to have 128 bits of adder, it takes very long time. 256 bit, double the time. It means I increase to 256 bit, the clock rate has to be half. 1 gigahertz becomes 500 megahertz. Oh my God, no one is going to buy your CPU, right? So based on this, would you spend time to optimize T carry or T sum? Any idea? You only have one chance. You have 2 circuits to optimize, right? 1 day before the project deadline, you find that you are too slow. You only can optimize either T carry or T sum. If you were doing the ripple carry, which one would you optimize?
Would it be the T carry because it's being multiplied by the n minus 1?
Exactly. Yeah.
So that way, if you optimize that, you're gonna have a better, more optimization.
Right. So bear this in mind. Very good, right? So later, if you run into a problem, say I am able to minimize the area, but at the same time, I need to sacrifice either T sum or T carry. Then you will sacrifice the T sum. Maybe make it a little bit longer. I don't want to sacrifice T carry, right? So you see that it's scale with n, okay, that I just mentioned. So this is not good, but this is easy and simple. And this is a good baseline for us to compare. Okay, any questions about ripple carry adder? Now, if no, then I just want to teach you a property called inverting property of adder. Now, let's see that. On the left, you have a regular full adder. A plus B plus C in becomes S and C out. On the right, something strange, but still the input is A, B, C in, S, and C out. It's just saying that you will get the same result if you put a NOT gate to all these ports. So what does it mean? On the left, I have S equals to a function. Okay, just a function of A, B, C in. Or C out equals to a function of A, B, C in. And what function is this? We discussed already. This function. This is the function for S. This is the function for C out. Okay? It's a function. Now, what does it tell us? Okay, it say that, hey, my output, if you log it, is the same as exactly the same function. Same function. But you put not B, not A, not B, and C in. Okay? If you not them and put into the adder, then the output will be just the not version. That is the inverting property. And that's, you can prove it, but that's all I want to talk about because we're going to use it later. But I hope you understand this is something very interesting. For an adder, turn out that it has this special property and you can use to save some of the logic. Probably not in your project, right? But what is so important? Now, if I remove this one, put the bar to here. If you remember how you implement all the pull down and pull up network, you can make pull down and pull up network the same. When you have this inverting property, what do I mean by the same? Think about LAN gate. When I have parallel on the top, I have series in the bottom, right? They are not the same, right? Right? One parallel and one series. But if you have this plot, that is because for LAN gate, A, B not equal to bar, log A, log B, and then take a bar. Okay, that is because of this. But if I have a function that is, I take the log of ABC and then take the log on the top, then it means I can implement the pull up and pull down network with exactly the same topology. And that also will simplify the circuit in some cases. Is that okay? Okay, just remember what I said, and then you will see it later. Okay. Okay, so now we know how to calculate a ripple carry adder, right? But we need to implement the 1 bit. It's not difficult. It's just complicated. Let's recall. Let's see what it is implementing here. First, look at the A, B, C. A, B are the input. C is the carry in, right? And then you come to here. Okay, it actually compute log C. That's why we need to have inverter to get the C not, C output, carry out. For this not carry out, right? Then it comes to here. And this one is a complicated logic you use to compute the S. You can verify it, but we will take a little bit study on what we are doing here. First of all, what is C out? We say that it is equal to AB. If you refer to my previous line, AC in plus BC in, right? So we try to make it as AB plus CI times A plus B. Okay. And so log C out equal to the whole thing log AB plus CI times A plus B. Now look at this. AB or CI times A or B. That is the pull down network. That's why we say this is not C out. And you just do the duality, right? This one parallel becomes series. So AB in series with this guy, you get this pull up network. Now this one, I have not used the inverting property of adder we mentioned here. We're going to use it, right? But this is just what we will do naturally. right? So that's why this computer C out. Is this okay? Now you already done midterm 2, right? Can someone tell me why I want to factor out the CI? What is the advantage of factoring out the CI? If I don't factoring out, I have CI times A plus CI times B, then I have CIA in parallel with CIB. What is the problem of doing that? Not problem or disadvantage. Basically, I'm asking, why don't I just do this? CI, A, CI, B, CI, C. Why don't I do that? Anyone want to help me? Really, no one? You already done your midterm.
We need larger transistors.
One extra transistor and I can.
They need to be larger.
What is larger?
C.
C. What is larger? Say again. Okay, I cannot hear clearly, but
The transistors need to be larger.
Transistor does not have to be larger, right? If you size it, how will you size it? Right, this will be 2, 2. This will be 2, 2, 2, right? Same here, I size it 2, 2, 2. But you're good. One extra transistor, more area. But at the same time, C out is larger. Why? Now here is confusing, right? This C out is not the carry out. I should say output cap is larger. Why? Because I have 2 CI, right? I have 2 carry in, 2 transistors. I have extra transistor. Originally, I only have 1. I only have 4 of them. Now I have 6. Make sense? Okay. Okay, so that's why we want to say that's just a very tiny question, very tiny problem, not difficult. But you see that it's important. You need to think about that when you design your adder. Try to save it. Save the area, at the same time, increase the speed. Now, why I put the CI on top? I can as well put the CI at the bottom. Again, 2 reasons. Any idea? You have answered this in the midterm.
Is it because your CI is your slower input, so that's why you have it closer to the output?
Excellent. Yeah, because we have been talking about this. So now this is something you need to remember when I talk about inverter, talk about adder. The first thing is that I hate CI. CI is the thing always slow me down. I need to improve it. Okay. You see that CI is the critical part. They always take the longest. I really rely on CI because AB, they arrive very fast. For this bit, AB arrived already. I'm still waiting the CI from 120 bit away to propagate to here. Okay, so we want to put, because CI is the critical part, critical signal. Okay, that's why I put on the top. And of course, in this particular configuration, if I put CI at the bottom, I bring AB to the top, then, right, if AB at top, I will increase the output cap. I have 2 transistors, 2 drain, right? Because now I have 2 drains here. Then I'm going to increase it. That's why I put CI on top, right? So you see that even this circuit is complicated. if you sit down carefully, think for a while, you find that you can have a lot of insights that other people do not have. Okay, now I hope that now you feel that this monster, right, is no longer strange to you. Everything looks so natural with a reason. Okay, although it's still not the best. Then let's look at the sum, right? What is the sum? Then for the sum, we need to write down the equation again. In this particular case, right, the sum, if you remember, is equal to A, B, C, I, and then any one of them, and then we need odd number of 1, right? If you remember, A not B, not CI, plus A, not A, B, CI, plus A, B, which one should not CI, right? This are all, every term has a not odd number of sum, right? But I'm not going to prove it. It turned out that this one equals to, and sometimes I say I don't go prove it. Actually, I never try to prove. I just take it for granted. You can try to expand and try to prove it. Equal to this. If you try to really plug in the equation, this is what we are using. Okay, and that's why we have this network, A, B, C, I, or C out and A, B, C, I, A or B or C, I. And then just do this, the duality for the pull-up network. Okay, and of course, this gives you not, right? Because we remember all the CMOS only implements the negation logic, right? So I need to add another inverter to get S. That's why this should be not S here, okay? Now here we want to see a few problems. Again, you can see, we put C out here because they are critical path, right? This is a critical path. So we put it at a higher place. I do have a question for you. Why we don't just implement this logic? Here, I need to wait for C out. I need to wait for this to compute in order to compute the sum. Why don't I just implement another logic to get this one? Implement this logic. Why I take this C out? Why it is okay? Why it is okay? Right, let's think about the full adder train. Again, C out is the critical path, right? We keep propagating. So even it take a longer time to do this sum, that is okay. Think about this. Yeah, C in, come in, carry in, carry out. Yes, now I wait for this carry out to compute S, but this carry out is still keep propagating. It takes longer to get S0, doesn't matter, because this one is still not ready. The only problem is in the last stage, this will take a little bit more time, but this saves a lot of logic. That's why we just take this one directly. So again, because C out is slow, right? In multi-bit, right? Okay, so that is okay to do this, right? But there are a few problems with this full stack, the full adder. I have 3, well, not here actually, long stacking PMOS. Do you see this? 4, that is very bad. How do I size it? 8, 8, 8, 8. So my drain capacitance is going to be very large and area is very large. This is bad. We don't want that. Remember the Elmos delay? Also, loading to the C out. You see how many loading do we have? This is going to the next stage, right? You need to drive the next stage. It becomes the C in of the next stage. How many? I need to drive 1 C in, 2 C in, 3 C in, 4 C in, 5 C in, 6 C in. 6 gate capacitor, right? Do you see what I mean? Any questions? this green one talking about 1, 2, 3, 4, 5, 6. This guy need to drive 6 capacitor in the next stage because this CL is the C-in of next stage. It has its own drain capacitance also. What color can I use? Here, 2CD, right? The drain capacitance of the inverter. And then, of course, plus the wire, right? So this is very difficult and very long because this is a critical path, okay? And then for carry, we have 2 stages, right? And then we also need an extra logic to do the sum. So this is not very nice, but it helps us to understand better. Any questions? Right, if no, then let's also look at what the good thing about this circuit, right? Let's first try to size it, okay? First of all, how do we size it? I told you already, this is 4, 4, 2, 2, 2, 2, right? And this is this I will put it 6, right? Just in case all of them are turned on, relying on this one. Right, correct? Right. So what is the logical effort for C? Logical effort for C in, right? It need to go into this 4 plus 2 divided by 3. So it is 2. Right. So this is the good thing that the logical effort for C in is not too much. And this is simple. The good thing about this this circuit is this is simple. So we can just optimize the carry out, right? And while we put CI on the top, we answer already. Okay, so this is one of the possible adder implementation. Okay, any questions? Now, with that, can we further simplify it? We can use the so-called inverting property. Remember that we just say that if you have the adder, this one is the same as, let me say again, it's a little bit difficult to say. This one, if I add a circle here, it will give you the same result, right? If you add a circle, right? So let's think about this. Here, at this point, so this point, what is this? This is CO0, correct? At this point, what is this? CO0 bar, right? So what we can do is, like here, we have CO0 bar, and this is CO0. So our goal is to fit CO0 to next adder, right? But however, I'm using the inverting property of the adder. I want to this time fit the CO0 bar into it. If this is the case, then I can just skip the inverter. Right, maybe I'll draw here, skip it. I don't need to add inverter because if I remove inverter, the output will become CO0 bar. And then this can fit directly into this circuit. And I know that the outputs of this one will be CO1, right? If skip inverter. So if I can cascade this version versus the inverting version, and then this version, inverting version in this even and odd manner, I can save the inverter of every stage. And that is the good thing about using the inverting property. Is this clear? A little bit confusion, I know, but think about that. This one, right, is full adder. The output supposed to be CO0. But if I add a circle, means I add another inverter, or it means I remove the inverter, it becomes CO0 bar, carry out bar. Carry out bar is what we want to fit into this one, right? As long as we can make all the input negative and negate them, then the output will be negated also. But if we remove the inverter, again, the output will be carry out 1. And this can go to this cell, and we just keep repeating. So basically, this train just remove all the inverter. Is this okay? Any questions?
Professor, I had a quick question about using at least like between like using an even and the odd cells.
Yeah.
So because we're inverting each of the inputs, wouldn't that add a significant amount of delay?
So
oh no, so yeah, never mind.
Good job, good point. Here it's just showing that we invert it, but in the real implementation, after we add inverter, we see that we have 2 inverters. We just don't implement them. So actually you save it. Right? Is that what you understand?
Oh, I was actually talking about like the inverters on like the A
and
B,
B?
and then S.
Oh, very good. That is also very good. But now, which one is the critical path?
Oh, I guess your carry out is still your critical path.
Right. So it doesn't matter. I take a little bit more to do this inversion, right? Because when I arrive, they are ready already. Except,
But even if it doesn't take more time, it still costs power and area, correct?
Oh, it does. You are right. Yes. But then on the other hand, here I save 2 inverter because the S is also saved, right?
Oh, I see. Okay.
No, S might not save. We don't really save the S. Sorry, S does not save. We only save 1 for the inverter. Yeah. So you do have an extra inverter. That is right. You are right. More area and power consumption. So it's a trade-off. Yes.
Okay.
Good. Okay.